Okay, hello everyone. Can you hear me okay? All right, that looks good. Well, welcome. Once again, this is class 5, which means that it's sort of bittersweet. It's unfortunately our last class, although there'll still be forum time and whatnot. And I have some, I hope, pretty cool stuff for you this week. This is, of course, week 5, and we're going to be looking at integrating funky anatomy. That is, things that really don't go together. And as a sort of hint to what's coming tonight, these are all examples of what not to do. But first, as always, before we dive deep into this subject, I wanted to see if there are any questions out there, either from last week or from projects we're working on or anything else we've covered in the course so far that we should get out of the way. And if you would be so kind as to type yes or something if you're typing a question so I know, I'll wait for you on that. All right, I see at least 2 yeses, so I'll be happy to wait just a moment. Sorry, I didn't have time to hack on tentacles or lobster claws onto this poor little proto-mammal. Maybe some other day. Isan is asking about the form of a bat's nose. Bats' noses are indeed really weird. I believe, I don't honestly know what they're for, Isan. I know some of them do use them, of course, as part of smelling. I kind of want to say, like, with such a big fleshy structure, I wonder if it helps them with their echolocation. And that might sound really strange because, of course, they don't hear through their nose. But part of echolocation is the differential response. That is how things echo from different directions. And believe it or not, everybody can do this to some degree. That's why when you hear noise, you can actually tell whether it's like to the left or the right or behind you, even though you might be like not with directional speakers. And the reason that works is because some of the sound travels through your head to the other ear. And when it does that, the difference in timing lets your brain filter it out but also recognize where the sound came from, much the way bats are doing, but obviously not nearly as good. So it might also be that it creates a focus of sound waves coming from the front at a specific speed, but I'm not sure whether it's that or whether it is just related to smell. I would have to look that up, and I will. I will drop that down so I can put that up in the forums for you. Because some of them have crazy noses. Okay, great question. Dinosaur Revolution is not apparently for sale. I have copies on DVD that they sent me since I was in it. It is available on certain tubes that you can go to and find episodes to watch. I believe the reason it's on sale right now is a recut version went to theaters or is going to theaters. And so I think they wanted to wait until that got through its showing before releasing any direct to TV or to DVD or whatever. Okay. Yeah, and that looks like a really good idea with the snake. The question is, would the snake need a part of the torso that wouldn't flex? And the answer is that would really help a whole lot, yeah, especially if there's a big sternum there. And I love the ideas of modifying it with not having to have a face that doesn't expand and stuff. I think that is fantastic. Oh, and Brooke thinks that my speculation has some basis in fact. I appreciate that, Brooke. And I think it seems reasonable. I just can't recall like a citation I came across. Okay, Isan. Yeah, yep. Okay, so I think we're on to something. I may have even read that, but if I can't cite something, you know, the scientist in me is like, I don't really know it until I can recall where it came from. So I will look it up for sure. Yeah, sorry, Igor, the quality is not really good on certain popular places to find video. You know, honestly, since I have a whole stack of Blu-rays for other specials and dinosaur shows, I don't feel like even the DVDs do it justice. I really wish I could watch it in like glorious high def. But for now, it is not to be. Hopefully later this year it will be out. Okay, great questions. But shall we go ahead and dive into today? Oops. I'm going to do a, oh, yep, we got one more question here. Oh, yeah, that's a good question, Charles. Let me add that to my list of things to do. Pterosaur back muscles. Yeah, I can get you some links to some pretty good muscle diagrams. Believe it or not, I don't work directly on pterosaurs. I keep up with the literature, so I know who to link you to, but I have not done any illustrations myself along those lines. So I can definitely get some reference up there. Okay, so today we have a agenda that looks brief, but it's got some interesting returns to looking at basic science to help you just grasp why some of these things are important. But they all have important design clarifications or details, so I think you'll like it. One, of course, we're going to do a really brief introduction to mixing anatomy. It's just kind of what we're talking about, what we won't talk about. Then we're going to talk about breathing and design. And I know some of you might be like, didn't we talk about breathing a lot already with ribs and stuff? But I promise this is not what you think it's going to be. This will go in a very different direction. We're going to talk, of course, about mixing anatomy as the main topic. Specifically, we're going to think about it from the tissue level first, just so that when we cover the big mixing groups, it'll be obvious why things have to work the way they work. And specifically, we're going to look at arthropods, whether insectoids or arachnids or other things, but things that have exoskeletons, how to mix exoskeletons into your creatures. And, of course, for those of you who are phylogenetically challenged, arthropods would include spiders, crabs, scorpions, cool things like that. And then we're going to also look at mixing tentacles into your creatures, which are mostly going to include octopi and squid and stuff, but we will look at sea stars briefly and see why they're probably not the greatest model. So at the end of the day, hopefully you'll have gotten to get a feel for how you can really go out that last 20% of craziness, but still do it plausibly if you want to start adding things that really couldn't go together on Earth, so to speak. All right. So briefly, we've already sort of looked at mixing disparate anatomies, obviously. Hey, Tom. You know, centaurs, griffins, obviously mix anatomies that don't ever go together in real life. But in a way, these aren't very challenging in some ways because they're mixing vertebrates. Like, they're all things that kind of come from a fairly closely knit group when compared to the vastness of the rest of life on Earth, let alone the various kinds of life that might appear on other planets. So while there are cool things you can do, even just with vertebrate anatomy, a saw-toothed shark obviously has gone pretty far down the wacky hole when it comes to things you can do without even mixing in exoskeletons or tentacles. Nonetheless, you can definitely get all... Oh yeah, here's another example in mythology. Actually, this is like the only example I can come up with, and this is still vertebrates. Nagas, of course, have both snake-like reptilian parts and sort of fishy parts sometimes, and people-like parts. Really not done very commonly. I think it's because it's kind of hard to do believably. Here, of course, is a design that has tentacles, and there are parts that are okay about this, but really it comes across as an animal with tentacles kind of superglued to the back, which in all fairness to 2D artists is indeed how creature effects artists have been doing it for years because, you know, you got to get them on somehow. But when it comes down to it, if you really want to have that freedom to do something like this or something like that, you should have that freedom. You just need to know how to approach it the right way to get results that will not ever result in an unintentional laughter, and will be scary if it's supposed to be scary. So how are we going to do that? Well, let's take a small detour, although it's leading us back there, I promise. And that's going to be about breathing, except it's not really about breathing exactly. It's about the implications of how breathing and muscles and size work together. So this is a lizard. No surprise there, but you notice how it has incredibly skinny legs. Those muscles are really tiny, and that's because the hips are really tiny. In fact, the hips are tinier than you would think because the muscles, believe it or not, bulge out from its tiny little hip bones. And these are actually the thickest way they go. They're even skinnier the other direction. Whereas if you look at animals that are warm-blooded, and by the way, the general consensus is that dinosaurs, like their living relatives, the birds and mammals, are warm-blooded to at least some degree. They have these massive sets of limb muscles. Granted, T-Rex is a bad example on the forelimbs, but they have huge pelvises and they have huge muscles, and this is not a coincidence. In fact, it's a telltale sign, and it's not size either. Here, for example, is the Komodo dragon, a very big lizard that let's just say you wouldn't want to run into in a dark alley because you would not be the one coming out. And Komodo dragons actually have relatives that got up to over a ton that were alive not too many tens of thousands of years ago, and their leg muscles are just as small. Whereas here's a rooster with a freak genetic mutation that causes it to live naked its whole life. You can see how ridiculously oversized its thigh muscles and its calf muscles are, even though they're hardly fast runners in the bird kingdom. And even though it's much, much, much smaller than a Komodo dragon, let alone a one-ton relative of not too distant past. Why is this? Oh, here's some internal evidence, if you will. Here's a Komodo dragon skeleton, and here is a tiny little ilium. These, by the way, are reconstructions by Gregory S. Paul, not by myself. And this is a dinosaur pelvis here. And that is a very big ilium, and that is a teeny tiny one. And it's not, again, to hold up the weight, because this is a smaller dinosaur or animal than that is. And it's not because these are faster, because it's not actually true. Lizards are usually just as fast as most birds or mammals of the same size. It's actually all about breathing and muscle type. So, and this really struck me watching the Olympics. If you watch, say, swimmers or runners or what have you, anytime you go for endurance, like say if you have the 400 or 800 meter swims, you'll notice they have to breathe every few strokes, and it's not until the very end that they really start kicking like crazy and keep their head down and just go for broke. Whereas if you've ever watched the 50-meter freestyle, which is like an all-out dash, they literally don't come up for a breath the entire time. They dive in, they swim, and they don't breathe until the end. Well, why is that? It's because when they're doing that short burst of activity, they're exceeding what can be supported with aerobic exercise, and they're doing anaerobic work. Anaerobic might sound like a fancy, sciencey word, but it's actually pretty easy to break down. You know what aerobic is? It actually really just means like with oxygen, and an just means without. So just really what it comes down to is you're doing work that is so hard that your muscles can't support it with your oxygen breathing system, and so you're building up lactic acid. And you have to stop this pretty soon because lactic acid is toxic, and if you don't, you will die, or at least have to lay very still for a while you breathe it out. Of course, you can train your aerobic capacity. Marathon runners do, swimmers do, and that allows you to go at a certain pace, essentially indefinitely, as long as you can keep up with it by breathing hard. Why are these issues important to designers and artists? Well, it's not just something you can do to get in shape or lose weight. It turns out that the muscles creatures have are directly impacted by how good your aerobic capacity is, and therefore whether you're warm-blooded or cold-blooded. You see, all these big muscles that mammals are so proud of actually, yeah, he does look ridiculous, actually suck. That's a funny thing, I guess, to tell the next guy you see like this. His muscles are pathetic. because there are different kinds of muscles. You've probably heard of them if you're into, like, say, sprinting. There's fast twitch versus slow twitch muscles. And fast twitch muscles are far more powerful for their size than slow twitch muscles are. The problem is that fast twitch muscles don't work aerobically. So the reason a lizard can be just as fast as a mammal, dinosaur, or bird of the same size despite having less muscles is because they don't have the metabolism to support aerobic work hardly at all, so almost all their muscles is fast twitch. And that means that they actually have a far higher yield of power for the same amount of muscle mass. So if you think about it, it's a trade-off. They can get away with much more power with less actual muscle that they have to support with eating, but the downside is they can't get away with it for very long. So because they can't basically support high levels of aerobic activity, cold-blooded animals end up with skinny little muscles, and warm-blooded animals end up with really large ones, which do let them be active, but they have to, like, put all the extra energy into supporting them and then supporting the aerobic system so that they can use them more constantly. Yeah, we'll go back for just a sec. Yes, flying animals are always aerobic, although there was a great design of an amphibian that could live in the water that probably could have gotten away with being anaerobic because it could simply return to the water at any time and not fly too far that were on our forums. And of course, flying fish actually essentially use this to a lesser degree. They mostly swim in the water, and they just take short flights trying to escape predators out of it. But yeah, flying animals have to be warm-blooded and have to be able to use aerobic capacity. Now, interestingly, some flying animals have a huge fraction of fast twitch muscles in their flight muscles, and they basically have to have, and this only seems to happen really in birds, but they have to have a system where the rest of the aerobic musculature and high performance blood system is able to swap out the lactic acid that's built up on short bursts of really fast flapping after they, like, say, take off or really climb. So yeah, so no, but you know, the funny thing is, if you were a lizard, almost all mammals, Remy, would look like they're on steroids. It would look like they have a ludicrous amount of muscles, and indeed, if you could create a T-Rex or a velociraptor that truly had lizard-like leg muscle power for the size of their muscles, they would be stupidly fast. They'd be like running around at like 50 or 60 miles an hour, and of course probably falling down a lot because if you're cold-blooded, you don't always process information as well as you can because of the lower body temperature, unless like you're just at the exact right temperature. But then they'd also get tired incredibly quickly and have to sit there, possibly for hours in the case of bigger animals, until the lactic acid went away. Okay, one other thing that breathing matters on. Right, somehow the Hulk has anaerobic muscles that just don't get tired. I don't know how it works with some sort of metabolic breakthrough. You're right, that kind of would have to be the explanation. So really giant insects obviously don't exist in our planet. And the reason for that is not, as some have speculated, that like exoskeletons somehow don't work at this size. Well, maybe not at this size, but there's really nothing holding back exoskeletons compared to endoskeletons. The real problem is that they have to breathe. And as we discussed in our flying class, most really small insects simply have a tube system that connects their skin into their bodies, and it just diffuses right across there into their like little watery bloodstream, and that's all there is to it. And because they're small, that works well. But bigger arthropods have to have solutions. So here's a horseshoe crab, and they have what are called book lungs down here. See these little flaps? And these move, and when it moves water in and out against these flat areas here, and there is little, again, blood in there that circulates through and then goes back into the system, and that facilitates a more effective exchange of oxygen into them. And that's actually one of the reasons here they are closed. that's one of the reasons why they can more effectively move both in and out of water, too, is they have this efficient breathing system that, as long as these are wet, works in both places. Spiders, even though spiders aren't necessarily big, also adopt a version of this internally called book lungs. And so they have holes on their abdomen that actually go ahead and support the air coming up into this moist internal area. Of course, it has to be internal here because it keeps it wet all the time. If they dry out, they don't let the oxygen get across into the bloodstream. And this is a far more efficient way of breathing than the usual, like, say, fly one with a whole bunch of little spherical holes all throughout the body, just piping air in at will. In scorpions, they have it too. These are book lungs visible on the bottom. Sometimes when people are looking for whether they're boys or girls, they mistake the book lung openings for the reproductive openings, which also in girls are down there, I believe. And the reason I bring this up is if you're making a giant scorpion or a giant insect, like, you know, for the next Starship Troopers movie or what have you, what you want to do is make sure you're taking that into account. And you could put it on the bottom and kind of hide it out of the way as long as you're thinking about it and it's there, but I would expect it to move because the bigger they get, the more challenging this gets and the more complex those internal lungs would have to get. So I would even expect, and this is of course not an exoskeleton animal, but it is an interesting idea. I would expect to see large, fairly obvious intake holes, maybe with like little softer tissue valves to close them off when they're inhaling or exhaling, on truly giant insects. And it's the kind of thing where if you're going to make, you know, the lobster that attacked New York, you really want to take this into account because they're not going to make it just scaling them up, you know, from something that works at a foot or two to something that'll work at like 30 feet or 100 feet. Okay, so in short, when it comes to really respiration, not just breathing, with vertebrates, limb muscles are small in animals with slow metabolisms, cold-blooded animals, and they're really big in warm-blooded animals or animals with high aerobic capacity. But because cold-blooded creatures use more fast-twitch muscles, they're actually equally as strong. They don't have the endurance. So like when it comes to arm wrestling, you know, an animal with fast-twitch muscles and much scrawnier muscles will be just as strong, but if they're evenly matched, they're going to lose eventually because eventually they won't be able to keep exerting themselves while like a bodybuilder who isn't actually any stronger despite having freakishly large arms will win just because he can keep it up or she can keep it up without like having to go comatose if they try too long. And if you think about this before you design and combine your anatomies, it can really help. There are actually basal dinosaurs with actually surprisingly narrow like thigh muscles and hips, bigger than lizards but pretty narrow, and probably shows that the earliest dinosaurs had kind of an intermediate metabolic rate, much the way primitive mammals like echidnas and some marsupials do today. So you can pretty easily come up with a dinosaur-like design or a mammal-like design that still has thinner leg muscles if you wanted to like make them living in a more amphibian-like lifestyle or just on a planet where that makes sense. And specifically, it's the kind of thing, once again, where if you're designing for a movie or TV where you want to think about how the creature has to act, get your hands on the script or talk to the director or something, because you can totally make a cold-blooded creature on a planet that will seem really alien and foreign and still be really active as long as it's in short bursts, you know, and really destructive. It's just that they can't do it forever, whereas if you have to have like a 10-minute chase sequence at the end that represents probably more than 10 minutes in movie time, you're going to have to go for something that has those bigger limb muscles in order to allow them to actually successfully pull off the scene. And of course, insects and things like insects, things with exoskeletons, have to breathe also, and the bigger they get, the harder that breathing challenge is. And it's why we don't actually see truly gigantic animals with exoskeletons here, is they've never actually specialized their book lungs to the point where they could do it. Now, animals with exoskeletons were heading that direction right about the time when vertebrates got on land and started taking over the land, there were 2-3 foot long, 4 foot long animals that looked, like, well, that were actually related to centipedes and millipedes and that were related to some sorts of scorpions and stuff. There were sea scorpions also that were not truly related to modern scorpions, like got up to maybe even like 8 feet long or more. So they were starting to like take on these size-based challenges, but we never got to see that because animals with backbones sort of took over the large charismatic megafauna role on our planet. But I really have little doubt that they would have solved it had they been the only animals like living on land for a longer period of time. So feel free to do this with your aliens. Just make sure that you address the breathing problem when you do it. And as a result, therefore, giant arthropods really need to have those breathing apertures or some other solution built in. And even maybe like if you combine anatomies, depending on which parts you're combining, you might want to make sure you're planning that out as well. So are there any questions here before we move on to the actual combining parts? Anything about breathing you want to know? Sure. Isan, dinosaurs are definitely, so there's this myth that there's like this gap between mammals and birds and like say lizards and crocs. If you actually look at basal metabolic rate, or like how many calories they burn per unit mass, if you will, per chunk of the animal for their size, the mammals with the that are sort of the most primitive metabolically actually overlap with the monitor lizards with the highest metabolic rates. There's no such thing as like an intermediate. Like the avian mammalian range is huge and extends all the way down to what we call cold-blooded. So it's sort of like a misnomer, and it's because these words were coined decades and decades ago before we actually had hard data on like calorie burning per size, oxygen consumption per size. We had to have fancy machinery we've developed in the last couple of decades to test that. So conceptually, we think of them as equal things. Oh, there's cold-blooded and warm-blooded animals, and we tend to think of one as like moribund and inactive and slow and dim-witted, and the other one is like awesome and fast and big and active, and like there must be this huge gap. But in reality, lots and lots of mammals, especially marsupials and the egg-laying monotremes, have really quite low metabolisms that are just barely above or just slightly above the highest levels of monitor lizards. And like monitor lizards are above, like say, iguanids and other types of lizards too. So you have this whole range. Now with dinosaurs, living dinosaurs, of course, have the highest metabolic rates because they're birds. But like even then, flightless birds have metabolic rates that tend to be much more in the normal mammal range, like what other, like say, dogs or horses or other placentals would have. And kiwis actually have a surprisingly low one that's still well above the lizard rate, but actually in the kind of upper part of the lower mammal range. Now, as far as like non-bird dinosaurs, the things we usually think about, most dinosaurs show the muscle types and other features that suggest they're somewhere in that middle of that sort of normal mammal range, probably not nearly as high as flying dinosaurs are today. But the earliest dinosaurs, the earliest meat-eating dinosaurs, the earliest two-legged relatives of like the sauropods have surprisingly skinny hips, which suggests that the very first dinosaurs probably were more like, say, the spiny anteater or the duck-billed platypus in their metabolism, where it was elevated a bit over like monitor lizards and crocs and what have you, but we're not up in what we'd consider the normal mammal range, which would be like you or your dog or your cat, which is like quite warm-blooded. So the earliest dinosaurs seem to have kind of an intermediate, lower warm-blooded physiology, although obviously we can't know for absolute sure. You can't stick a thermometer up their cloaca and check, for example. But they grow faster than lizards do today. They have expanded hips, just not very expanded hips, and they have some other features when it comes to like air sacs and breathing. But quickly, in all major dinosaur lineages, those hips expand dramatically to obviously support aerobic muscles, which means they obviously were now moving into the sort of normal mammal range. Whether it was exactly as high as dogs or cats, obviously we can't say, but somewhere in the normal mammal range once you get through most of the Mesozoic. And of course, some groups of meat-eating dinosaurs that were covered in feathers, like say Velociraptor, actually developed very surprisingly bird-like breathing mechanisms And by that I mean actually flying bird-like breathing mechanisms, which suggests they're actually in the upper part of the mammal range and maybe getting towards the lower part of the flying bird range. Yep. Now again, that doesn't mean that Velociraptor was like faster than other meat-eating dinosaurs, but it might mean that if they had to, they could sustain their activity levels even longer. And in humans, we're really kind of lazy. Like, we don't have to go running every day to survive predation or catch food. So we tend to think of aerobic capacity as something that's very, very malleable. You have people who train for it and run marathons. But in reality, usually most species have a much narrower practical range because there are just things you have to do every day to survive. And so, the human way of thinking about it is like there are people who use treadmills and there are other people who sit around in front of computers, like possibly many of us, and that therefore aerobic capacity is hugely variable. It's probably a very artificial construct of modern society, and probably when you think about creature design, you should expect that most of the creatures within a species are going to have a pretty similar range, and it's going to be more decided by their metabolic range than not. I mean, if you have a zoo full of creatures, you could have lazy ones for sure, but that's not the normal wild condition.